I'm excited to tell you about our project at Google, about a system we developed within the last 1.5 years. It's called Janus, about optimal flash provisioning for cloud storage workloads. So here, I show you the view inside a Google data center. It's in Iowa. It has 115,000 square feet of space. That's larger than one soccer field. So hypothetical, if you assume it has 100 petabyte of storage, that would mean if it's like 1 terabyte drives, there are 100,000 disk drives. So that's a lot of things which are moving there. They can hold a lot of data, but unfortunately, the trend is that the disk drives get larger and larger, but they cannot handle more I/Os. That's why we need to separate the cold data and the hot data and use flash, which has a much higher I/Os rate. And this talk is about separating the data and optimally allocating the flash to the workloads. This just shows the general trend. So disk drives are slow and are getting larger but not faster. Flash, on the other hand, offers much higher I/O rate, but it is expensive. Here, we look at the thousands of workloads which we have in such a large cloud environment, such a huge storage systems. There are thousands of users and applications like indexing, ad serving, email, video processing, and many, many more. And each of these applications do have several jobs or many jobs, which often have their own separate data. We looked at just the mean age of what one job is reading the data. And you see there's a huge variance here. But like maybe 30% of the jobs read data which is in average only 1 hour old. So that's a key property we are using, focusing on the young data which is read most often. Janus is working with the main Google storage system, which manages the disk and flash access. It's provisioning and allocating the flash based on historical workloads, and I explain why we came to these decisions for the system. It uses sampled RPC traces to look at the read RPCs. It then optimizes the flash allocation between the workloads, and it does two things with it: a real-time placement decision for the file system, and in addition, it's used for offline provisioning and planning purposes. There's also a lot of related work. Our focus here is on a distributed cloud-scale environment. We do use RPC tracing, but since we are in such a huge environment, we need to focus on sampling, so only sampling of RPCs is possible for us. There's a lot of work on caching, but the constraints of the existing system and due to the distributed nature made our choices to focus on insertion on write and to use an approximate FIFO. I explain later what this means exactly. There have been economic studies about the cost effectiveness of flash. So here, for the first time, we show that in a large cloud environment, it is cost effective if we consider that the workloads are different and we optimize the allocation among the workloads and focus on the hot data. Here, some insights into the economics. We assume that data on disk is IOPS limited, and flash has basically unlimited IOPS. This is practical for our systems and our workloads. So if we go to a store somewhere January this year, you can buy maybe a 100 terabyte disk drives, which has 150 IOPS per second. So you can assume you can buy 1.5 IOPS on a disk per dollar. On the other hand, you can buy 1 gigabyte of flash per dollar. So if you put an entire workload into flash, it's becoming cost effective if this workload has 1.5 gigabytes, 1.5 IOPS per gigabyte. So in 2008, there was a study where this number was 60. So much higher IOPS rate was required to become cost effective. So we analyzed all our workloads in our system, and we got this plot here. The green dot stands for one workload. The 2008 break-even line is the top line, 60 IOPS per gigabyte. And even for our workloads, none of the workloads is above the line. But the 2013 break-even line is lower. And there are now several workloads which are cost-effective to place entirely in flash. But this is not all what we are doing. By separating out the hot data from all the workloads below, we get a further cost benefit by just moving some parts of the workloads data from disk to flash. So I come now to talk about our system, Janus. Here first some decisions we took upfront about the insertion of data into flash. The usual approach probably you think of is inserting data in flash when it's being read. But in a distributed system, this is quite expensive. It takes time, and first of all, you need to communicate this. So our approach is to insert the data directly into flash when it's being created. Not the data of every workload, but of those for which it's beneficial. And we are motivated by this by seeing that a huge fraction of the read operations goes to the very youngest data. After the insertions, we need to decide what data to evict. There are different options. You can do it what is least recently used, or what was first inserted. So we took the second choice, primarily because it's a distributed system. The system Janus itself can handle both LRU as well as FIFO. And in the end, and in the paper, there's also a comparison about the results. FIFO actually slightly performs worse than LRU. We even simplify the FIFO. Rather than checking how much capacity is used and how full our FIFO is, we already decide when new data comes in for how long it should stay in there, based on the historical analysis. So we determine the TTL, the time to live, for every file going into flash at the very beginning. So here's an overview about the system again. So new files come in, they go to flash or to disk. So that's the first question. Should it go to flash or should it go to disk? If it goes to flash, we need to also determine how much flash does a workload get. Or this also determines how long should the data in flash stay. If we give more flash to a workload, then the data can obviously stay longer. To come to the answer to these questions, and here we are talking about thousands of workloads, and we want to do this automatically and optimally, we do first some input data collection. On the one hand, we scan the metadata to identify by the age of the data how much data there is, or how much data this workload has which is younger than a certain age. Secondly, so this is on the right side, you see we do some sampled RPC analysis of the read operations. This gives us a statistic of the age of the data which is accessed. For a given age, how much read operations go to data which is younger than this age. Given these statistics, we develop a cacheability function, a characterization which is specific for each workload. I will show this in the next slides and give the formal definition. This is used by the global optimization problem, which then answers the 3 questions I posed before. Should it go to flash or to disk? What should be the amount of flash for a workload? And how long should the data stay in flash? So step to the first row here in this diagram. How do we get to the cacheability functions from the data we collect? The cacheability function maps the amount of flash to the flash read rate. So this directly shows the benefit of assigning flash to a workload. It's derived from 2 functions, or the 2 statistics. First, we create this function for a workload, which shows you for the age how much data is younger than this age. It's always increasing with age. Then from the sampled read analysis, we look at how many read operations there are which go to data younger. So we get this function here, the red one. And it's very often, or in almost all cases, that the red line is above the blue line. So that means that most read operations go to younger data. From the 2 functions, we can look up for a given amount of flash or given amount of data size, which goes to flash, for how long can the data stay in there, and then look up how many read operations go to this data. So we have done this now for 1 data point, for 1 amount of flash on the right side. If we would do this for all, we would get a function like this one. This is a cacheability function, so it shows us for the amount of data, how many read operations go to data, to the youngest data of this workload. Very characteristic is this steep step at the beginning, so that you need to move only very little to data to flash, and you get a lot of read operations handled then from flash. This is just the input to the main optimization problem, to the allocation of the flash to the workloads. The primary goal is to maximize the flash read operation rate to reduce the disk IOPS. That is what sometimes enforces us to not use disk to the full capacity, because there are just too many IOPS. So the problem is formally defined, as here. The instance consists of the workloads with the cacheability function. Each workload has 1, and the priority weight. These priority weights we introduce to give some priorities to some workloads, mainly for latency reasons. Then, as input, there's also the total flash capacity. The task is to allocate flash to the workloads to maximize the weighted flash read rate. The solution is bilinear programming if we assume that the cacheability functions are concave and piecewise linear. If it is not concave, we handle this in the second part of the paper. So we get a quick solution to just maximizing the read operations rate. But in practice, this would not be sufficient for our application, as we also need to consider the write rate. In these data centers, the flash is used heavily. It's not comparable with any consumer electronics. So there are constantly some workload writing to it. So as a new problem, we have a secondary goal, bound the flash write rate to reduce the flash wear. It also had actually, practically we experienced in some cells some performance issues when the write rate was too high. It was impacting even the read latency. The problem, so here's the problem definition again, which we solve of this optimization problem. To bound the write rate, we first introduce a write probability for the workloads. That means not every data of a workload is written to flash. Only a certain fraction. Namely, we sample the new files with a certain probability to go into flash. This sometimes makes sense if we assign, well, one point is that it's reducing the write rate, but it also keeps the data which goes to flash for longer in the flash. And there are certain pipeline jobs which start reading after a certain amount of time their data. So there you would get more benefit by keeping it longer in there. It is an exception, but it does happen. So this write probability is a new optimization parameter. It randomly selects new files for flash to write only a fraction to flash. The instance then is, again, the workloads with a cacheability function. And in addition, we need to know the write rate of the workload. We are given a bound on the flash write rate, and we are given the total flash capacity, the flash available to be used. The task is to allocate flash to the workloads to determine the write probability for each workload, such as to maximize the flash read rate. But of course, consider the bound on the flash write rate. This is a mathematical optimization problem. And here you see the formulation. For each workload, we have two primary variables. xi, the amount of flash we allocate to the workload, and pi, the write probability, introduced in the last two lines here. The objective is to maximize the flash read rate. And here you see the probability and the amount of flash allocated in the first line. And it's part of the cacheability function psi. There are two constraints, the bound on the write rate with the write rate and the write probability. And the second constraint is the bound on the total flash. To solve it, we relax the constraint on the bounded write rate. So this means we remove the constraint from the list of constraints, but insert a penalty factor to the objective. You see here the new objective at the bottom. This shows the penalty factor at the end and the constraint which is removed. To solve it, we iterate over the penalty factor lambda to get the best solution which satisfies the write constraint. Removing this constraint is an important step because now the write probabilities only show up in the objective, and we can compute what would be the best write probability for a workload independent of all the other workloads, just depending on the allocation size. This allows us, after a convex approximation, to run some greedy algorithm which solves this in almost linear time. And that's pretty important because we deal with a huge number of different workloads. And of course, the more workloads we have, or the more we partition all the workloads we have already in sub-problems, the more choices the optimization has and the better the solution also gets. Interesting about the convex optimization approximation here also, which is required if the function is not concave, is that in the final solution, you actually get a solution where at most one workload you make a mistake in the approximation. This is all described in the paper. So I now come to the last part, to the evaluation of our results. So Janus is a system which is in production, and it is doing the online flash allocation used in Colossus, the main Google file system for the last 6 months in multiple data centers. The optimization results are also used by dozens of teams to influence flash purchasing and flash planning decisions. These are the questions we address in these evaluation sections. How does the past predict the future? How does it compare to alternative methods? What is the impact on the bound on the write rate? And in the paper, there's also a comparison between FIFO and LRU. First, how well does the past predict the future? Well, our system, as I explained at the beginning, it needs to do some historic analysis and then make immediate decision on new files come in. That's where we actually got the name from. So Janus is an ancient Roman god who is the god of the beginnings and transitions. And you see here a picture. It's looking forward and backward. So it's looking back to the past and forward into the future. There is some variation, obviously, but it's limited, which is shown in this graph here. So we did a long-time analysis of 30 days for our historical analysis. And then we applied this for the used this in the optimization and calculated the flash parameters used to run the actual assignment or allocation of flash and running the flash disk system. This gave us then the actual hit rate on the y-axis. And you see it's pretty close to one line with some 7% difference here. But overall, it's not varying too much. So our workloads are rather stable and only changing slowly in the average. Here you see for one workload, and we did a lot more detailed analysis, but I can show only one line. Over 2 days, how does the read rate of this workload, now that it's using flash, compare to the predicted read rate? So sometimes it's below, sometimes above, but overall, it's in that range, and this is sufficient for our application. Now I have some comparison with alternative allocation methods. How does the optimized results compare? So we took here 2 cells. The first cell has low workload variance, so the workloads are all pretty the same. The last one has a higher workload variance. And the first thing we did is that we simply allocated the flash in proportion to the total data size this workload has. So you can see the flash hit rate here, 14 and 15%. Next, we looked at one single FIFO. So there's one FIFO in which we put the data of all workloads. So the data of all workloads stays the same amount of time in this FIFO. The TTL is not different. It gives some improvement. Actually, for cell B, it's already quite some improvement. Next, and this was getting much better, if we allocate the flash proportional to the amount of reads the workload does, we get these numbers, 26 and 64%. Finally, we look at the optimization. So this is how we're doing it optimally. Optimally using all the input we get, right? So it's the best allocation to maximize the read rate. And as you can see, it's the best one. And if I compare this just with the number where I treat each workload the same, then I get a 47% and 76% improvement compared to the method, the best method we compare against, which treats each workload the same. Now let us look at what the impact is on the write rate. Here you see the results for 4 cells. The write rate percentage of the total write rate is at the bottom. If there's no bound, you get the points on the right, and you get pretty close to 95% of the total write rate. But as you constrain it then to, say, 40%, there is a small decrease. And it was surprising, and as well it's important for this method to work, that the decrease is only small. It's small for up to this point. Of course, then if you decrease it further and further, at some point you are not allowed to write anything to flash, so you can put very little data in there only, and it has to stay there forever, and it's getting cold after some point of time. So this is this graph, and there I'm getting to the conclusions already. So to conclude this talk, the Flash has become cost-effective in a large-scale distributed file system if it is used selectively for some workloads. So our system Janus does this long-term workload characterization as a first step. It works with these characteristic cacheability functions and uses them to formulate and solve an optimization problem to allocate the Flash for the different workloads, and it maximizes the Flash read rate, but can also consider bounds on the Flash write rate. Thank you for your attention, and I'm ready to take questions. In the audience, there are also my co-authors, Arif, Murray, Eric, and Shudong, and they can also take questions in the break or later at the Google booth.
Any questions?
Hi, I'm Venkat from Facebook. So you mentioned you characterize different workloads and do allocations based on, like what is the domain?
Yeah.
Like what is the application? Like how do you identify the application? How many do you have? And like can a single product that is a Google end product pick different application IDs for different categories of like the data? Like for example, in Facebook, there's a lot of data that has temporal locality. But your friend list doesn't have temporal locality. It doesn't matter when you friended someone. Like the access never really changes. There's really no locality for some types of data. So
So you can look at many things to partition your workloads, right? So this system is actually in the whole storage stack. It's pretty low. So it's there's higher storage systems above it. And they can like put something in the name, but the advantage is that they don't really know, and we do the analysis for them. So we don't just, and the more you partition it by taking anything you like, the more workloads you get, and the more flexibility the optimization has, right? So in general, the better, the more workloads you have, the more you separate the data, the better the optimization results get.
Is that separation done by looking at the analysis, or is it done by like different product teams with picking different identifiers for identifying different parts of their data?
The focus is on doing this automatically, looking at the metadata of files, but you can also think of, and we tried this one, to give application insert additional hints, like give hints how to separate this data.
Sorry, one.
So in the interest of coffee break, one short question with one short answer.
Hi, good presentation. My name is Kishore from NetApp. So I had a follow-up question from the previous one. So you said some workloads are good for caching and some are not. So can you give, based on what you saw, what are some of the workloads that were good for caching and the ones that are not?
Well, we do this very abstractly, right? This is the advantage of the system. So we never really looked at where it's actually coming from. We were just very surprised with the result to see that this many are actually how well the optimization method is separating, right? But you can think of it like maybe there's some video backup systems where it's actually just to transform into a different file system, which is happening all the once in the time. Or sometimes there are some logs which are not really read. So of course this depends. Some logs are read heavily or so on. But I guess there's many things which are cold and many things which are hot, and we separate them automatically.
Okay, then let's conclude the session. Thanks, speaker.